Okie dokie. So now, this was really just the introduction, motivation, what kind of stuff could we be doing? And now in the second part, I wanted to look at the actual discovery procedures or algorithms, right? And again, it's a huge body of research, and I'll just show you, I'm not even going to say highlights, I'm going to show you some of the simple things with some nice ideas inside of them, right? And so we're going to go through this typical, trifecta of unique column combinations, functional dependencies, and inclusion dependencies, in a sense, going from the easier to the more and more difficult problems, computationally complex problems, okay? So let's start with unique column combinations. I mean, here's a little bit of a more formal definition. So given a data set and a schema, unique column combination is a subset of the schema, so a subset of the attributes, or columns, such that for any pair of records, the values for those columns are unique, right? So are different. So you look at two records and you say, okay, the values for my key have to be different. So if you look at this particular example here with 3 columns, a very trivial example, and so A is a unique column combination, clearly. AB as well, AC as well. BC taken together is unique, and ABC together is also unique, of course, right? And in the relational model, we always have also kind of the assumption that if you take all attributes together, they have to be unique. There are no duplicates in your data. No record is repeated. But in reality, that can happen as well, okay? And then you might have some non-uniques. So B is not unique, C is not unique, the rest, any other combination is unique, right? And probably most of you already figured out, well, I said A is unique and AB is also unique, but who cares if AB is unique? A alone is already unique. So we're usually looking for so-called minimum uniques. So minimum uniques are those for which there's no subset of columns that is also unique. It's an obvious concept, right? Everything, as soon as you have all minimal uniques, these two, you can derive all other uniques from them, right? You take A, you add any other column, and it's still unique. You just don't need to write it down, in essence, right? And usually, let's say in a database system or so, you are kind of interested in the minimal uniques. You wouldn't define a primary key with more columns than necessary, typically, I would say. Okay, so this question here, since we're talking about databases, gives a rise to a little bit of a difficulty that we have to figure out how to deal with null values or missing values, right? This is a common phenomenon. You could say it's data errors, but there could just be null values because there's no value there. There are many different semantics. So for instance, the semantic of being unknown, date of birth, you just leave it empty because you don't know when a person was born. That's a null value. Or not applicable. So driver license ID for children, it's just not there. It's not that you don't know it, it just doesn't exist, right? And there are other semantics, right? There are many reasons. The question is, how does that affect your algorithm? How do you define uniques? And there are two, in essence, there are two lines of thought or two semantics that we have to look at, right? So if you look at this table right here, so A is clearly unique, right? B is clearly not unique. What about C? C unique or not? What would you say? There's always the perfect computer science answer, but maybe you have a different one. So what would your answer be? I mean, you can't go wrong here, right? So is C unique, yes or no? So is C unique? Who would say it's unique? Okay. Who's more skeptical? Say it's not unique? Okay, some of you guys. Okay, the perfect answer here that I would always recommend to all of you in any of these situations, say, it depends, right? That's like, right? The other, so that's why I tell my students also in database class. So either you answer with it depends, or you answer for optimization purposes. Because that's the other answer in database systems for almost everything, right? Okay, anyway, so there are different semantics. It depends, right? So if you're looking for primary keys, if that's your goal, you're looking for unique column combinations that might be primary keys, primary key cannot have a null value, right? So anything that has a null value, you can discard right away, you're not interested in them, right? So for that purpose, C is not unique, right? But SQL databases have different semantics. So for instance, normally SQL says two null values are not equal, right? So if I have unknown values, I'm not going to assume they are the same. I'm going to assume they're different. I don't know what they are, but I'm going to assume they are different. Under those semantics, C is indeed unique, right? If that's how you think, if that's what you're interested in, then you would say C is indeed unique. B is not unique because it has 2 3s right here, right? But that result would say if you have a completely empty column, that's a key candidate for you, right? Because it has only null values, so it must be unique, or that's your definition. So it's kind of strange, but that's what you get with this semantics, right? But SQL grouping, for instance, groups all right now, or okay, SQL grouping groups all null values into one big group. So there the semantics is null is the same as null. So if you say group by C, you'd get one group containing the tuples of this of these two null values. And in that case, of course, A is unique, and BC together is also unique, right? So it's kind of counterintuitive. You can always find examples that don't look right, but they make sense under certain semantics. Go ahead.
So the column of nulls is unique, I agree, but nothing prevents one of the nulls from taking a value like X.
Yes.
In which case, the column would not be unique.
Yes.
So C cannot be part of the unique, even if null is not equal to null.
Oh, here you say that's a mistake?
Yeah. Because null can be equal to X. At that point, it's not, the column is not unique.
Okay, but if you do a comparison of these two.
Right, but in terms of possible values.
Yeah, okay, yeah. Right. But if you let's say count distinct values here, so then that would be the semantics. Anyway, yeah. So there's books about the problems of null values and etc. Right? So I will not dive into this anymore. All of the algorithms I'll be presenting and all of the approach and all the papers basically always work with both of the semantics. It's kind of a setting in the algorithm what you're interested in. Right? That's all there is to it. But you have to be aware that this is a problem. And if you run an algorithm twice with different settings, you might get different results because the semantics might be configured differently. Right? Just keep that in mind. Okay, so what are we looking for? So I showed you earlier this North Carolina data set. This was the table that we zoomed out on, et cetera, et cetera. These are voters. And we analyzed this one. And this this column combination is a minimal unique. Voter registration number, zip code, race code. Yeah? So that's already interesting. You would, voter registration number alone should be unique, I guess, right? It sounds like it should be, but it's not. This is minimal, so you cannot remove any of these without losing uniqueness. So that could be a pointer towards a data error. These typical algorithms that we run find all minimal unique column combinations, and as a byproduct, also the maximal non-uniques. So this column combination here is not unique. These are over 60 columns. If you put them all together, it's still not unique, which is weird. And it does include the voter registration number right at the beginning. You add all the other stuff to it, it's still not uniquely identifying a voter, which again points to a possible data error, right? Yeah, go ahead.
Do you also have, as we had with the relaxed dependencies, does that also apply to minimal uniques to maybe see if it's more of a data error rather than?
Yeah, you could do that. I mean, we didn't do this here. Absolutely. So exactly. So this effect could happen if there's accidentally really a duplicate in your data. Then everything is not unique, even these large combinations. Absolutely. But this is not all the data. So there are 30 more columns. And if you add any one of those, it's suddenly unique. So there's a problem here in the data somehow, right? And yes, indeed, you could say, okay, then please output all the duplicates for this here. Why is this a non-unique? Show me all these examples and then go ahead and clean them. And you could probably relax. You could say we have a relaxed dependency saying I'm going to allow a few duplicates. So it's unique, it's almost unique, and then we wouldn't find that one, but maybe something larger. And then, by the way, this North Carolina voter data, I mean, you know that US people don't have much about privacy. I mean, this is straight from their FTP server, which is still public. This is the directory of the FTP server of the North Carolina State Board of Elections. If you go in there, you find letters, birthday invitations from the mayor to his buddies. This is a catastrophe, really. And I've every time I give this talk, I say this, but nothing's changing. I mean, of course, I'm not writing to that State Board of Elections because I want this to stay up. But you can see all sorts of stuff in there. And it's really an FTP server. You can click around. And the link, it's not that I found it. There's a link on their website saying, go to the data, and then they just serve you this FTP site. Yeah, but birthday invitations, I'm not sure if that's covered by... Anyway, maybe it's all fine, but personally, this is person data with their race, what they've registered for, their religion, address, everything is in there. So if I were living in North Carolina, I would not vote, period, or not register as a voter. Anyway, okay, so here's a chart about the problem size, okay? Number of candidates we have to check to find out, is that a unique or not, okay? So if you have one column, you need to check one candidate. If you have 15 columns, right, there are 15 candidates of size 1, right? 105 candidates pairwise, et cetera, et cetera. And the larger, of course, your candidates, your candidates get, the more of them are there. So there are 6,000, more than 6,000 candidates of size 6. So column combinations of size 6, okay? And then if you add them all up, if you're saying, if your table has size 15, in principle, you have to check 32,000 candidates. That's the number of combinations that exist. This is simple, and all put together, it's just simply 2 to the power of n, right? That's the number of combinations that exist. Minus 1, why? Because we're not looking at the empty combination. We don't care about that, okay? The largest size, again, is like, as I said earlier, it's kind of in the middle, right? If all the minimal uniques are cover exactly half of your columns, right? Then this is the potential number of minimal uniques. So your result size is already potentially exponential. Typically, of course, it's not, but it can be. So, in a sense, you can see how difficult it is to find. Okay, so how do you go about this? I've already shown you this lattice here, or this type of lattice. So here's this lattice again with 5 columns, A, B, C, D, E, and then column combinations of size 2, 3, et cetera, et cetera. Now, of course, the big trick here is pruning. You don't want to check every candidate. If you find A is not unique, but AD is unique, then all supersets of AD you don't need to check anymore because they are not minimal, okay? That's already kind of the whole trick here, right? We're pruning a lot of the search space. If you can find out that one column is already unique, you can prune away half your search space, half the search space. That's great, right? Here, this guy here is a quarter of your search space, right? Very, very useful. And the cool thing is it also works the other way around. If I have, for some reason, found out that BCDE is non-unique, then, of course, all its subsets below, the color doesn't really show up on the slide, all of the subsets below are also non-unique, right? If there's a duplicate record BCDE, then, of course, BCE alone or B and D, et cetera, they're also non-unique, right? So you can prune both directions, which is useful. And this also gives rise then to various algorithms. Some go bottom up, some go top down, kind of depends. There's also a zigzag algorithm that kind of goes turns from the top and the bottom. But in essence, what you're always doing is you're traveling through this lattice, checking for candidates, and making sure you're not checking candidates that you can prune, right? And when I say checking a candidate, I mean going into the database and finding out, is it unique, yes or no? And again, this is very useful. This knowledge is useful that as soon as you find a counterexample, you can stop, right? And if columns are not unique, it's actually quite likely that the counterexample appears quite early, right? So it's this strange column that you say everything is unique, and the very last value is a duplicate. I mean, sure, that can happen, but often you can stop, after maybe 10 comparisons or so, you'll find a unique. Okay, so this validation is very fast. The only place it's slow is where it really is unique, because that's the point where you have to go through all the data to find out, okay, actually it is unique. But that's okay, because that's the stuff you're looking for, so you're maybe willing to spend a little bit of time for those, right? And you want to make sure that they are indeed unique. And running through column combinations is something that we know a lot. Based as in computer science or in data mining, because the a priori algorithm is a very good example of running through combinations of things and pruning, and it fits perfectly to this particular example. It's the traditional data mining algorithm for association rule mining, the a priori algorithm, and it works here as well. So the idea is you're at some level, you found out what is unique, what is not unique, and then you use that knowledge to figure out which candidates at the next higher level do I even need to check. Right? And if something is unique, then obviously the stuff above it I don't need to check anymore. So I only need to construct my examples of the next level using the non-uniques of the prior level. This is how the pruning works, right? Okay, so you're level-wise, you start with the single columns, then you check pairs, then you check triples, et cetera, and at some point you find no new combinations, then you're done, right? So here's the basic idea. Again, this is really purely the a priori idea. So if you know the a priori algorithm for association rule mining, this is exactly what we're doing here. So just very briefly show you the idea. You don't want to generate too many combinations. So for instance, the combinations ABC, ABD, ACD, and BCD, they are all could be used to generate ABCD by adding the missing attribute. So you've checked ABC, you've checked ABD, you've checked ACD. So if you just look at that guy and say, okay, this is not unique, I'm going to go one level up. There are many ways to go up that level to find the candidate ABCD. So one thing is you don't do it 4 times. You make sure you only do it once. Okay, so I'm not going to check this guy 4 times because there are 4 different ways to expand this guy. This is obvious, but you have to figure this out. You have to do it actually, right? And so how do they do it? They use prefix-based generation. So you're only going to do it by combining column combinations that have the same prefix. So ABC and ABD have the same prefix of size n-2. AB is the prefix. And then you're going to expand those to ABCD, right? And you're not going to bother with those guys here. They don't have the common prefix. Okay, this is just the idea of how you algorithmically actually go about it. Okay? And then what the authors of this particular paper, not the a priori algorithm does it all right, but the authors of this paper to check unique column combinations didn't see is that once you have generated ABCD, you can check for all subsets and find out are those unique or not. So you could do some more pruning even, right? Which they don't do, but it's easy enough, and then you're faster still, right? So how does this then look, right? So this is our lattice again. You do checks for the individual columns. Are they unique? And then you might find out, nope, they're not unique. You can clearly see that this is a light green, right? And that's white. Okay. Sorry, here it's obvious, on this screen not. Anyway, so you go one level up, you check all those candidates, and then you might discover, okay, those are all unique. You also know they're minimal unique because you've already checked everything below. Okay, so you're kind of done here. And those are all light green non-uniques, but you don't know if they're maximally non-unique. They're just not unique, right? So you can prune away all that stuff, right? And then you go a level higher and look at those guys. They're all non-unique, unfortunately, so you go one level higher, check that guy, and then that one is maximal non-unique. You know that because this one here is unique, so the other one must be maximal non-unique, and then you're done. This is how the algorithm works, right? And it's okay. You can do better, but it's a reasonable approach, very simple to implement, and kind of a nice approach, right? So characteristics, bottom up. Best case, all columns are unique because then you're done right at the bottom, right? Worst case is there are no uniques, then you have to then you can do no pruning at all. You run through the entire lattice and never prune anything, and in the end say there's no unique. That would be really a bad case. So a priori in principle is exponential in n, right? Worst case complexity, but typically, of course, it's quite fast. Okay, so this is one basic idea, and it's really one more nice example of how this cool a priori algorithm can be applied to other areas. So next I want to show you one quick algorithm that we did to improve this a little bit. Right? What we did not like is this tedious level by level going up, checking all the candidates at that particular level. So the idea was that we do a random walk through this lattice. So the idea being we go straight up. We don't do level by level. We check one column, and then if it's not unique, we go up. If that's not unique, we go up again. So we kind of try to get a head start going up the lattice until the point where we hit a non-unique, unique. Then we say, oh, okay, we found a unique. That's great. We don't know if it's minimal, but we have something. And then the idea is, should be on the next slide. Yeah, exactly. The idea is that we then, kind of go up and down in that lattice to find the border of uniques and non-uniques. I'll show you the visualization in just a second, right? So if the current combination is non-unique, we go up. If the current combination is unique, then we go down, and we kind of go up and down through this lattice, do some pruning, efficient validation. So if this is the lattice, then in a sense what the algorithm does is, let's see if this works. finds this border, right? Of course, this is a visualization of something that doesn't exist in the real world, but if you think of it that way, that's exactly how the algorithm works. So in a sense, right, we maybe, I don't know, we start here, we go straight up, and from that point on, we kind of walk through the lattice, right? And it's actually very efficient. And as I said earlier, it can be parallelized nicely because you can start at 5 different points and walk up. You have 5 different servers, and then they inform each other what they found. So that actually works also pretty nicely in parallel, right? So we're, in a sense, getting a head start. We're not going level by level. We just go straight to the interesting part.
Sorry, just a question.
Please.
I didn't really think about this enough, probably, but is it better to start in the middle because the information gain might be higher, so to say?
Well, you don't know what I mean, sure, as I said, there are bottom-up approaches and top-down approaches. We could start at the very top, also a possibility. If you kind of have an idea where your uniques will be, then that's where you should start, I guess, right? But I mean, often you will have individual columns that are already unique on their own, so it kind of makes sense to start at the bottom. And plus, I mean, we walk up fast. It's not like we look at the whole bottom, so it doesn't really matter. I mean, starting in the middle, just says, I'm saving 3, maybe, validations. And each validation, by the way, so I'm not explaining this at all in this talk, but we're talking about a millisecond or so. So each validation is super fast because they're very efficient index structures to do this. So the validation steps are super duper efficient. So it's really the search space kills you, not the actual validations. Okay. Yeah.
Is the outcome local optimal or global optimal?
All the algorithms I'm showing are exact in the sense that they produce all minimal unique column combinations. Whether this algorithm is optimal or not is completely unclear. I mean, it's not optimal. I mean, there are better algorithms, so it's not optimal, actually. But we have been trying to, with a theory group at HPI, trying to characterize the computational complexity of these problems. And the problem is always that it depends on the data. So to say anything about an average case complexity, maybe, you need to know the characteristics of the data. You have to model them somehow into your complexity model. And that's super duper difficult. So we can often show that the problems are very, very difficult, but in practice, we're very, very fast. So that tells us data is mostly nice to us, right? They're not worst case and they're not average case. Somehow they're good. They lead to good results very fast. So we haven't been able to find a good model of how data is usually distributed. Anyway, so this was the algorithm. Here are some measurements. We don't want to go into this. It just shows you how this algorithm is better than everything that we ever saw before. Fine. The interesting point to me is this measurement where we said, okay, this is the runtime of the algorithm. That's the red bar. And the blue bar is the number of unique column combinations that we find. And the nice thing is you can say it scales with the result size, right? So in that sense, you could say it's optimal, right? But this is not a proof, and this is just one experiment. But it's kind of a nice result to say, okay, if there's more to find, we need more time, clearly, right? And if there's not much to find, we're also very fast. So that's kind of a nice property. But again, it's not proven, it's one experiment, okay? Good. Any other questions? That's it for unique column combinations. Key candidates. It's the easiest problem. It's also conceptually also the easiest. You're looking for uniques, and if you have a duplicate, you're done. Okay. So functional dependencies, the next big thing. So I have to show these slides that a student of mine, Ciavash, he's no longer a student of mine, he's a professor now. He made this really nice motivation of what functional dependencies are all about. Just 2 slides. So the game of dependencies. So there's a spoiler alert here. If you haven't seen Game of Thrones season 1, this is a massive spoiler. Okay, so go outside or so, but I'm assuming either you're not interested by now or you have seen it. So this is a database of persons living in Westeros, right? So you have the person, all the guys. They have a lineage or a house, with their family in essence. They have a hair color, they have a religion, and they have all sorts of other attributes that I'm not showing here. Okay? So if you go about looking for functional dependencies, you could find these. So first of all, the person determines the lineage. This is obvious. So given a person, you know that person's lineage because the person is the key. The key functionally determines everything else. So that's not a surprise, right? We have a key here, and so obviously if I know, you know, I don't know what their names are, Jamie, then, actually I know them, okay, Jamie, then it's clear what lineage he has, what hair he has, what religion he has, etc. Right? But there are more interesting ones, like the lineage determines the hair color, so two persons with the same lineage will also have the same hair color, or two persons with the same religion and same hair color will have the same lineage. You can do all sorts of kinds of discovery. These are functional dependencies, right? So in the story, and Ned Stark goes ahead, looks at these functional dependencies, and interprets them as quality constraints, right? So he says, well, you know, obviously, if you have the same family or lineage, then you have to have the same hair color. So this should always be true, obviously, right? It's a functional dependency, right? But then, in reality, of course, Joffrey is born. Yeah, indeed, he's also supposedly of the House Baratheon. But lo and behold, he has blonde hair. So what does Ned Stark say? Well, I think Joffrey violates my database constraint. And of course, stupidly, he tells the Queen Cersei, and we all know the consequences, head on a spike. You know? Okay, so you know, they have real-world consequences, these functional dependencies, but I hope now you kind of know what it is. In essence, what we're saying is if two tuples or two records have the same value in one attribute, they also have to have the same value in the other attribute. Go ahead.
I have a question whether this kind of dependency is similar to causation.
To causation?
Is it the same thing?
I guess no. Divesh is shaking his head. It's a correlation. Why is it? It's a one-way correlation. Yeah, but isn't that causation? Okay, I haven't thought about this. Let's take that offline. It's a good question. Okay, Divesh has thought about it.
They could be both the effects of the same compound, they might not have been.
Okay, yes, there might be a confounding variable. Is that what you're saying? Okay, good. Yes. Okay. Good. And in this case, anyway, it's not true, right? So, okay, good. So, okay, let's get back to business. So this is the kind of the formal definition, but I've told you before, right? X determines A. X could, by the way, be more than one column. So, you know, a set of columns determines one column. So you could say, for instance, a first name or zip code and street determine city, for instance, or so, right? You can have combinations of that sort. Again, we're looking for minimal functional dependencies, right? So if first name, last name, date of birth determines your age. No, that's a stupid example. Determines the city you live in. Then first name, last name, date of birth, and a place of birth, of course, also determine where you live, but it's not interesting, it's not minimal, right? You're looking for the minimal ones again, right? So the goal of all these algorithms is, given a relation, you know, one big table, find all minimal, non-trivial functional dependencies. With non-trivial, I mean, of course, it's always true that A determines A, but you know, who cares, okay? And we're using, heavily we're using inference rules for pruning, transitivity, right? If X determines Y and Y determines Z, there's, you know, functional dependencies in a transitive sequence, then of course X also determines Z, and that's a candidate I don't need to check anymore. But that's the kind of pruning we will be doing, right? And that's also, that's the kind of the basic of all algorithms. If you don't have such cool ideas, you could come up with a naive solution. So the naive solution, the baseline, if you will, would be the following. For every column combination, that could be the left-hand side. And then for each attribute, that's going to be the right-hand side of the functional dependency. And then for each pair of tuples, if they have the same value on the left-hand side, but they don't have the same value on the right-hand side, then it's not a functional dependency you break. Otherwise, you give that as a functional dependency. Of course, this algorithm is the absolute catastrophe, right? This is exponential here. This is linear. This is quadratic, right? So, you know, this is, and then, so that's quadratic, and this is then again linear in the number of records. Right? So yeah, it's completely out of the question to execute this. And this runtime also shows in the number of candidates. So now you know what this chart kind of is supposed to show. And in this case, for the same 15 attributes, we'd have 245,000 candidates that we'd have to enumerate. And keep in mind, 15 is really small. It's just because that fits on the slide. So 50 or 60 or 70, that would be more realistic for a typical relation. Okay? The cool thing is, we can still use this lattice to model functional dependencies. So we don't have to learn too much new. The interesting thing is here that the edges of the lattice reflect the functional dependencies, not the nodes. So for instance, this edge right here asks the question, does A determine B, right? Or this edge right here asks the question, does A, B together determine E, right? So those are our candidates. And the pruning, in a sense, works the same way, right? If I know A determines B, this edge here, then I'm not interested in whether A, B determines C, because B is already determined by A, so I can deduce this transitivity. So if AB determines C, then A alone already determines C, so it's not minimal, right? That's the kind of pruning you can do. And the same works the other way around. The non-FDs, if I know something does not determine, then of course a subset, if BCDE does not determine, if BCD does not determine E, then of course B alone cannot determine it either, right? So you can prune in both directions. Same story. And again, you can use a priori style enumeration to run through all your candidates. I won't show you how this works, but this is kind of what these algorithms do. There's lots and lots of algorithms, and they all differ in the fine tuning they use special inference rules for functional dependencies to tune a little bit more, prune here, prune there. But in essence, the main rule is always this transitivity and minimality pruning. Okay? So these are column-based algorithms in the sense that they go through all column combinations and do the checking. There's a whole bunch of other algorithms that are row-based. It's actually quite interesting. So what do? They look at pairs of rows and see if something has the same value. So if you look at let's say the first two rows, Thomas and Sarah, right? They have the same surname. Maybe it's a bad example. I need two people with the same name. Oh no, it works, right? So these are non-functional dependencies, right? So surname, postcode, city, mayor together do not determine the name, right? Because the name is the same and the rest is different. And you can do all sorts of things, right? Name, postcode, city do not determine surname. Surname does not determine any of these, etc., etc. How do you get them? You look at in principle at least, all pairs of rows. Okay? If you look at all pairs of rows, you'll have all non-functional dependencies, and from those, you can derive then the functional dependencies. There's an efficient algorithm to do this, right? So what is the difference between these two approaches? One was column-based, the lattice. The other one is row-based. The row-based algorithm is very efficient if you have many columns. It doesn't care how many columns you have because you look at all pairs of rows and each pair you can look at very, very fast, right? It doesn't really matter if there are 20, 30, 50 columns. It's all super fast. The problem is, of course, you have to look at all pairs of rows, so it's quadratic in the number of rows. The column-based approaches of the previous slide, they are very efficient in the number of rows. I said it's like a millisecond to check a candidate. It's super fast, but the number of columns is the problem because your lattice gets very wide, right? So you have two different algorithms with two different properties, and now here's something that I've seen in literature often, and this is usually a very good idea. You just do a hybrid approach, right? You say I have two different algorithms that are pretty good at different situations, right? So I use a hybrid algorithm. The most trivial hybrid algorithm just looks at the data set. It says, oh, it's pretty wide, many columns. I'll probably use the column efficient version, right? Or it's pretty long, it doesn't have too many columns. I'll use that version. That's the most simple version of a hybrid algorithm. So we developed a little bit more interesting variant of this, basically saying we're going to implement both and we're going to switch back and forth between them. We're going to start with this one, looking at pairs of records, and already seeing what can I glean from some pairs of records. And at some point, you're looking for more and more pairs, but you're not learning anything new, right? There are not many new functional dependencies or non-functional dependencies coming up, so it's no longer efficient. Then we switch over to the column-based algorithm over there, right? And we get a head start because we can already prune a whole bunch that we learned from the row combination. So we get a head start there, then walk up the lattice. And at some point in the lattice, we're no longer efficient, so we're looking at candidates and we're not finding many new functional dependencies. So we're kind of stuck. I mean, we're going up and up and up, but we're not pruning much. So suddenly we realize that, and then we switch back here. And the cool thing here is we know exactly what to look for because we know which candidates over there we couldn't properly validate in a sense. So we're saying we're looking for column combinations that have the same value in column Y because that's where I'd like to progress over there. Right? So you can do a very focused sampling suddenly here for pairs, and then you go back and forth until you're done. Right? And so usually you go back and forth 5, 6, 7 times or so. It's not like you do this 1,000 times. You know, they really help each other, and they're very fast. And so I wanted to show you the results. You don't have to, you know, I'm very proud of these results, but I'll show you some better ones later on. So this is very fast. This is fine. You don't beat all other algorithms. This is great. That's what you want to do in research. But I want to point to this part here, which warrants some discussion. So we've looked at a whole bunch of data sets. And we're very fast at finding all functional dependencies. The interesting part is how many functional dependencies do we actually find? So this is a bit scary, right? So here's a data set, 63 rows, 1,000 columns, 500 kilobyte, we get 178,000 functional dependencies. It's a bit crazy, huh? So, I mean, and they're true, it's, you know, validated, you know, it's all fine. So this raises the question, why do we care? What do we do with 178,000 functional dependencies? No human is ever gonna look at them and say, oh, I like that one not so much, right? So clearly we need research, and there is research being done on ranking them based on their genuineness. This is what I had mentioned earlier, right? We're interested in genuine functional dependencies. These are all valid, but they're not genuine. They're just coincidental, right? And so this is just what I wanted to point out, right? So the numbers get pretty wild, okay? And here you can also see, this is all in seconds, right? So you can see, you know, even such a good algorithm, you know, we need, you know, minutes, and some of the slower algorithms need, you know, hours. And you can see the data sets are all very small. 3 megabyte or so, right? So even with a small algorithm, you can, a small data set, you can run, you know, many hours on this kind of a problem. So I'll give you a sneak peek. This is not published yet. This is what a student of mine, Tobias, has been working on in the past months. This is also an FD discovery algorithm using a solution for the hitting set problem. So one, you know, bear with me just very briefly. It's a very nice idea. It's not a new idea. It's just adapted to the functional dependency detection algorithm task. So you have a little bit of a table, ABC, with some values. These are the true functional dependencies that we're looking to find, right? And the interesting thing is, what you can do is you can calculate so-called difference sets by sampling the data. So you look at, again, pairs of records, just like before. And then you can see for the first pair of records, they differ in A and C, right? They have different values in A, and they have different values in C. So that's a difference set is AC. And you do that for all pairs. So you know all combinations that are different, right? And then what you do is you look at individually at the different right-hand sides. So you're wondering what determines A. Which attributes can I put here on the left-hand side that determine A? And the cool property is it's the hitting set of these difference sets. Okay, the hitting set of these different sets are all attributes or attribute combinations that hit each difference set together. So A alone is already good. This is obvious. A determines A. It's trivial. But also C is present in both. So C is a hitting set. And so C determines A. A little bit more interesting over here, right? So A is not a hitting set because it's missing here. C is a hitting set. C determines C. Who cares, right? But also AB together is a hitting set. All three are hit by AB. And so AB determines C, right? And the cool thing is this hitting set is an NP-complete problem, but there's super fast solutions for this. There's very, very fast solutions. So all the work that we need to do is create those different sets. We can do that based on a sample. And then we run the hitting set algorithm, and that solution will then point us to the samples that we have missed, and then we can continue a little bit of sampling, and we're very, very fast. Here are some results, just so you can see this. So this high FD algorithm I showed before was really state of the art for a long time, but suddenly we're up to many factors faster, which I never thought. So the message here is, keep looking, right? Even if you have a good solution, there's even better solutions out there. So I was very happy about this result simply because I wouldn't have expected that there's that kind of improvement still to be done after many, many years of research. Okay, last one. How many minutes do I have? I mean, we could skip this part.
We're running a little bit, 10 minutes, about 10
Altogether or for this part? For this part. For this part, okay. So I think we can skip this. We're already behind. This is a nice closure. And then the last part, we'll do a break now, is on applications. Okay, so thanks.